Hi, this is Rhiannon, and my presentation will be on the theory of relativity. The theory of relativity is meant to make sense of the measurements of the speed of light. The Michelson and Morley experiment was published in 1887 by Albert A. Michelson and Edward W. Morley and performed in Cleveland, Ohio. The experiment made an attempt at detecting the relative motion of matter through the stationary ether wind. The experiment's negative results are considered to be the first strong evidence against the ether theory, which was that there needs to be a space-filling substance, ether from the Greek meaning upper air, in order for the spreading of electromagnetic and gravitational forces. Basically, 19th century physics said that things, just like surface water, need something supporting it in order to move across it. Ever since the development of special relativity, theories using substantial ether haven't really had a place in modern physics. Michelson had conducted his own experiments in 1881 with a device that he had designed to be sufficiently accurate in detecting ether flow, a device that was later to be known as the Michelson interferometer. The interferometer sent light, either yellow from a sodium flame, which was used for the alignment, or white light for the actual experiments, through a half-silvered mirror to split the light into two beams traveling at right angles from each other. The beams would travel out to the ends of long arms to be reflected back into the middle by small mirrors and recombine in an eyepiece on the far hand side of the splitter. The idea was that if the Earth were traveling through an ether medium, a beam reflecting back and forth parallel to the flow of the ether would take longer than a beam reflecting perpendicular to the ether, because the time gained from traveling downwind is less than that lost traveling upwind. Michelson didn't observe the fringe shift that he'd expected, and he concluded that the idea of stationary ether would have to be rejected in favor of complete ether dragging. Others later pointed out to Michelson that a much more accurate and tightly controlled experiment would have to be carried out in order to find a definitive measurement of the ether wind. Then, in 1885, the collaboration between Michelson and Morley started. The two science professors set out to confirm with higher accuracy Fizeau's 1851 experiment on Fresnel's drag coefficient, improve on Michelson's solo experiment, and to establish the wavelength of light as a standard of length. In 1886, Michelson and Morley successfully confirmed Fresnel's drag coefficient, a result which also acted as confirmation of the stationary ether concept, and made them both more hopeful of finding the ether wind. In their improved version of Michelson's 1881 experiment, light was repeatedly reflected back and forth along the arms of the interferometer, increasing the path length to 11 meters, a length at which the drift would be about 0.4 fringes. The apparatus was assembled in a closed room in the basement of the heavy stone dormitory, eliminating most thermal and vibrational effects. The apparatus was built on top of a large block of sandstone about a foot thick and 5 feet square, which was then floated in an annular trough of mercury. Use of partially monochromatic light, the yellow sodium light, during initial alignment enabled the researchers to locate the position of equal path length more or less easily before switching to light. This experiment became what has been called the most famous failed experiment in history. Michelson and Morley reported their measurements to be as small as 1/40th of their expected displacement. They ceased their ether drift measurements and started to use their newly developed technique to establish the wavelength of light as the standard of length. The results of the experiments on the relative motion of the Earth and ether have been decidedly negative. The null result was further substantiated by the null results of other second-order experiments of a different kind, namely the Troughton-Noble experiment of 1903 and the experiments of Rayleigh and Brace from 1902 to 1904. These problems and their solutions led to the development of the Lorentz transformation and special relativity. Special relativity is the structure of space, time, and electromagnetism. The main point of it is that the speed of light is absolute, and that as an object approaches the speed of light, the time around it slows to a crawl with mass becoming infinite and the object itself shrinking. So if you could travel at the speed of light, time around you would be frozen. Then space and time are supposedly interchangeable, hence four-dimensional space-time. This is how someone traveling near light speed could appear to age not at all, while someone on the planet that they just left could have aged 45 years by the time that the traveler gets back. General relativity is supposed to throw gravity into that mess, with the whole space-time is curved. Albert Einstein formulated the theory of special relativity by 1905. He focused on the kinematic, or motion foundation of the theory, and the modification of the notion of space and time, needed away with the stationary ether's role. His theory came to the rescue when Isaac Newton's law of gravity incorrectly predicted the orbit of Mercury. The place in its orbit where the planet came closest to the sun didn't quite move the way that Newton's law had said that it would. The idea that energy and mass are equivalent and transmutable, E equals mc squared, is one of the consequences of the theory. Einstein took several years before he came up with the general relativity as a way of incorporating gravity. It's a synthesis between Newtonian gravity and special relativity. Spacetime is curved, meaning that gravity is a distortion of its structure. Anything moving through curved spacetime is pulled from a straight line path, although there isn't actually a pull, it's just a distortion or bend. Some of the results of which are the rays of light bend in the presence of the gravitational field, and that clocks run slower in deeper gravitational wells.